Welcome back to AI Codecast. Today, we're doing a deep dive on the Maximal Square problem. Um,
Okay.
you can imagine you've got like a satellite image, right, of
Yeah.
farmland,
Right.
but it's data. It's not just a pretty picture. So ones represent farmland, zeros represent everything else.
Okay.
And the challenge here is, how do we find the biggest square, like the biggest possible square patch of just pure farmland in all that data?
Yeah, it sounds pretty simple when you just say it like that, but it's actually a problem that has like real world implications. This sort of pattern finding is used in image processing, data analysis, even things like self-driving cars where like recognizing clear areas is crucial.
Right. The stakes are a little higher than just like helping some farmer measure their fields then.
Yeah, exactly.
So how do we even begin to tackle this? I mean, I imagine we can't just like eyeball it, and especially with a huge data set.
Yeah, you're absolutely right. The most straightforward approach is called brute force, which is kind of exactly what it sounds like.
Or
We're just going to try every single possibility.
brute force. Well, that sounds thorough,
Yeah.
but maybe not the most elegant
Mhm.
solution. So how would that work, like practically?
So imagine you start at each one in the data and you like mentally draw a square outwards, expanding it diagonally until you hit a zero. You do that for every single one, keeping track of the biggest square you found so far.
Okay, so you're saying like start at 1, 1, try to expand outwards. If you hit a 0, stop.
Right, exactly.
Then go to the next one and keep going.
Yep.
I can see how that would get the job done.
Right.
But it also sounds incredibly tedious, especially with, again, like massive amount of data.
Yeah.
Wouldn't that just like take forever to compute?
You're hitting on a crucial point: efficiency. Brute force is like using a hammer when you need a scalpel. It works, but it's not the most graceful or time-saving approach. In fact, in like the worst case scenario, the time it takes could increase exponentially with the size of the data.
Right, okay.
We need a smarter solution.
Okay, so if brute force is the hammer, what's the scalpel in this scenario? What's the smarter, more elegant way to find that, to find our biggest square?
So that's where dynamic programming comes in. Dynamic programming is all about breaking a problem down into smaller, overlapping subproblems and building up a solution step by step.
Dynamic programming. I always love how that sounds so dynamic.
Yeah.
But how do we actually apply this to this very specific challenge of finding our biggest square?
So instead of like hunting for the biggest square directly, imagine building a table.
Yeah.
We call it a DP table. And each cell in this table will store the size of the largest square that ends at that corresponding position in our original data.
Okay, so it's like we're creating a map of all possible squares, building block by building block.
Precisely. And the key is that the size of a square at a particular position is limited by the squares above it, to its left and diagonally above left.
So it's like we're only as strong as our weakest link. Like if one of those sides is shorter, then the whole square can't be any bigger. Kind of like a Jenga tower.
Yeah, that's a perfect analogy. That's exactly how we figure out the value in our DP table. We look at the size of those three neighboring squares above, left, and diagonal, find the smallest one, and then we add one for the current cell.
So we go through the entire image cell by cell, building up this DP table.
Yeah.
Then what? How do we actually find the answer from the table?
So the beauty of this is that once the DP table is complete, the largest value in that table directly represents the side length of our maximal square. So no more tedious searching, we've essentially mapped it out.
Okay, that is elegant. I have to ask though, isn't building a whole new table, isn't that kind of memory intensive? Especially if we're dealing with a really big image, a lot of data.
That's a great question. You're right to be thinking about space complexity, especially when it comes to large data sets. And, the 2D table does require a significant amount of memory. But what if I told you there was a way to optimize it to achieve the same result using much less space?
Optimization. Now you got my attention.
All right.
How do we slim down this solution?
So instead of storing the entire 2B table, we can actually cleverly use just a single 1D array and still get the same answer.
Really?
It might sound like magic, but it all boils down to recognizing a pattern in how we calculate those square sizes.
Okay, I'm all ears. How do we pull off this 1D array magic?
The trick is, when we're figuring out the largest square size at a given cell, we only actually need information from the current row and the one right above it. We don't need the whole table history.
So we're basically like compressing our calculations, just using the bare minimum information to move forward.
Right.
Kind of like a rolling window.
Exactly. The 1D array keeps track of the current row's progress, and then we use a single variable, let's just call it prev, to temporarily hold the value from the previous row that's relevant to our current calculation.
So we're ditching an entire table and just using a single array and one extra variable. That seems almost too good to be true.
Yeah, it's pretty cool.
Can you walk me through how this actually works in practice?
Absolutely. Let's take an example. Imagine we're looking at like a cell, say in the third row, second column. To figure out the largest square size there, we need three pieces of information. The largest square size ending at the cell directly to the left,
Okay.
which is in our 1D array.
Right.
The size ending at the cell directly above,
Okay.
that's where prev comes in. And then the size ending at the cell diagonally above left,
Gotcha.
which is also in our 1D array, but from the previous row's calculations.
So we're essentially doing like a little dance with the data, grabbing those key values from the current row and the one just above it.
Yeah.
Kind of like constantly shifting our focus, but just keeping the most relevant information in view.
Precisely. And then we take the minimum of those three values, add one for the current cell itself, and that becomes the new value in our 1D array at the current position.
Okay.
And we repeat this process for every row, and just like before, the largest value we encounter along the way represents the side length of our maximal square.
That's incredible. So we're getting the same answer, but using significantly less memory. It feels like we've really optimized this solution. Is there a catch though? Does this 1D array trick like always work?
It's important to remember that this specific optimization is really tailored to problems like this, where the optimal solution at a given point only depends on like a limited number of neighbors. It's not a universal solution, but it highlights the potential for space optimization in dynamic programming.
Okay, good to know. So it's still a powerful technique. And it's always good to be mindful of those memory constraints, I guess.
Absolutely, especially in real-world applications, where you might be dealing with massive data sets.
Right.
That's where these optimizations can really make a difference.
Speaking of real-world applications, can we switch gears a bit and talk about how we might actually code this? I'm more of a visual learner, so seeing it in like pseudocode might help solidify these concepts.
Of course, yeah. Let's sketch out the logic for both like the brute force and the dynamic programming approaches without like getting bogged down in, specific syntax.
Right. Just the core ideas.
We'll stick to the core ideas.
Perfect, because my coding skills are more enthusiastic beginner than seasoned expert.
So let's start with the brute force method. Imagine like a function called find largest square that takes in our data matrix as input.
Okay.
The first thing we do is initialize a variable called max size to 0. This variable will keep track of the largest square that we've found so far.
So max size is our champion, like the reigning king of squares, until we potentially find a bigger one.
Exactly. Now, we need to loop through every single cell in our matrix. For each cell, we check if it's a 1.
Right.
If it is, we use another loop to try expanding outwards diagonally from that cell,
Okay.
checking if all the cells along that diagonal line are also 1s.
So we're doing that like mental ruler thing we talked about earlier, right? Seeing how far we can stretch that diagonal line of 1s before we hit a 0.
Precisely. If we encounter a 0 during our expansion, we stop and calculate the size of the square we were able to form. If that size is bigger than our current max size, we update max size to this new champion.
So we're constantly comparing our current square to our reigning champion, looking for a new winner.
Right, and we repeat this process for every single one cell in the matrix. By the time we're done, max size will hold the side length of the absolute largest square we were able to find.
Okay, so that makes sense. Very straightforward, but I can see how it could become computationally expensive very quickly. What about the dynamic programming approach? Is the pseudocode drastically different?
It has a similar structure, but the logic is a bit more nuanced. So we'll have a function, let's call it max square, that also takes our matrix as input.
Right.
And instead of just a single max size variable, we'll create that DP table we discussed earlier.
Right, our handy map of potential squares.
Yeah.
And remember, we can optimize this later to use a 1D array instead of the full 2D table.
Right. So we'll start by filling our DP table with all 0s. Then, just like in the brute force method, we'll loop through each cell in our matrix.
Okay, so I see some parallels here. Like the looping part seems pretty familiar.
Here's where the logic diverges. For each cell, if it contains a 1, we look at the values in our DP table. At the positions corresponding to the cell above to the left and diagonally above left, we find the minimum of those three values, add one to it, and that becomes the new value in our DP table for the current cell.
Right. It's that weakest link concept plus one, just like we talked about.
Exactly. And if the current cell is a 0, we just leave the corresponding value in our DP table as 0. Once we've gone through the entire matrix, the largest value in our DP table will represent the side length of the maximal square.
It's amazing how we're essentially like building the solution incrementally,
Yeah.
right? Like using information from the cells that we've already processed.
Yeah, absolutely.
It's so cool. And don't forget, we can optimize this for space by using a 1D array and the pre variable to store the necessary value from the previous row.
Yeah,
So the core logic remains the same, but we're just being more efficient with our memory usage.
exactly.
All right, I think I'm starting to see the beauty of this dynamic programming approach.
Yeah.
It's elegant, it's efficient. But before we get too carried away, I want to address something that often trips people up when they're, actually coding these solutions. Edge cases.
Edge cases, those pesky little scenarios that can throw a wrench into your otherwise, perfectly crafted code.
Exactly.
You're right, they're important to consider.
So what kind of edge cases should we be on the lookout for with this maximal square problem?
So let's start with the most obvious one. What happens if our input matrix is empty? What if it has no rows or no columns?
Right. Yeah. Our code needs to be able to handle that gracefully and not crash trying to access elements that don't exist.
Exactly. We need a check right at the beginning to handle this. If the matrix is empty, we simply return 0 as the largest square size. Another edge case is like a matrix that's filled entirely with zeros.
Makes sense, yeah. Our code needs to recognize that there are no squares of ones to be found
Yeah.
and return 0 accordingly.
Yeah.
Are there any other kind of like tricky situations we need to watch out for?
We also need to consider matrices that have only one row or one column. These cases might seem straightforward, but we still need to be careful with our looping and indexing to avoid going out of bounds.
So empty matrix, all zeros matrix, single row, single column matrices. Those are our edge case watchdogs.
Precisely. Thinking through these scenarios before you start coding can save you a lot of headache during the debugging process.
Definitely, yeah. So we've covered a lot of ground here.
Yeah.
We've discussed the problem itself. We've explored both the brute force and the dynamic programming solutions, even delved into pseudocode and those crucial edge cases.
It's been quite a comprehensive exploration of the maximal square problem, wouldn't you say?
Yeah, absolutely. But before we wrap up this deep dive, I have one final thought-provoking question for you and for our listeners. We've been focusing on finding the largest square, but what if we changed the game a bit? What if we wanted to find all the squares of a specific size? Could we use these same techniques to, like, say, identify all the 2 by 2 squares of farmland in our data?
That's a fantastic question. And it really highlights the power of understanding the underlying principles behind the algorithms. It's not just about memorizing solutions, it's about adapting them to new challenges.
Right, right. Okay, so let's play with this idea. If we're looking for, say, all the 2 by 2 squares, how would our brute force approach change?
So the core concept would stay the same. Instead of tracking the largest square we find, we'd simply iterate through the matrix and check if each cell is the top left corner of a valid 2 by 2 square, filled with ones.
Okay, so we're still sliding that mental ruler across the image, but now we're looking for like a specific measurement instead of just the absolute maximum.
Exactly. We'd essentially be checking a 2 by 2 window at each cell to see if it meets our criteria.
That makes sense for brute force. But what about dynamic programming? How would we tweak that to find squares of a specific size?
We'd need to adjust what information we store in our DP table, or in this case, our optimized 1D array. Instead of storing the size of the largest square, we could store a Boolean value, like either true or false.
Interesting. So true would mean this cell is the top left corner of a 2 by 2 square of ones, and false would mean it's not.
Right.
But how would we update these Boolean values as we move through the matrix?
Our update rule would shift to focus on checking the current cell and its 3 relevant neighbors above, left, and diagonally above left. If all 4 of those cells contain true, then we mark the current cell in our DP array as true, indicating that it is indeed the top left corner of a 2 by 2 square.
Ah, I see. Okay, so we're still building up our solution cell by cell, but the information that we're storing and how we update it is tailored to this very specific goal of finding those 2 by 2 squares.
Exactly. And just like before, we could use our space-saving trick with the 1D array and the prev variable to keep things efficient.
This is really eye-opening. It's like we've gone from like a single solution to a whole toolkit of techniques that can be adapted to variations of the same problem.
That's the beauty of understanding algorithms on a deeper level. It's not just about the specific steps, but the logic and the patterns behind them.
I couldn't agree more. It's about, developing that algorithmic intuition, that ability to see the connections and the possibilities.
And that's what AI Codecast is all about. Empowering our listeners to not just understand code, but to think like coders.
Well said. On that note, I think it's time to wrap up this deep dive into the maximal square problem. It's been a fascinating journey, exploring different solutions, optimizing for efficiency, even considering those pesky edge cases.
Yeah, it's been a pleasure sharing these insights with you and our listeners. I hope everyone walks away feeling a little bit more confident in their ability to tackle algorithmic challenges.
And a huge thank you to our amazing community for always bringing such insightful questions and creative solutions to the table. You inspire us every day.
Absolutely. Keep those brilliant minds working, everyone.
If you enjoyed this episode, be sure to subscribe to AI Codecast for more deep dives into the world of algorithms and coding. We've got plenty more challenges to explore together.
And don't forget to check out the show notes for links to the source material, additional resources, and ways to connect with us.
Until next time, happy coding, everyone.